Class 2. Work, Energy and Power. Syllabus. First, work, energy and power with their relation with force. Scope of syllabus. Definition of work. W is equal to Fs cos theta. Special cases of theta is equal to 0 degree, 90 degree. W is equal to mgh. Definition of energy. Energy as work done. Various units of work and energy and their relation with SI units. Erg, calorie, kilowatt hour. An electron volt. Definition of power. P is equal to W upon T. SI and CGS units. Other units. Kilowatt, megawatt and gigawatt. And horsepower. P is equal to 746 watt. Simple numerical problems on work, power and energy. Second, different types of energy. Example, chemical energy, mechanical energy, heat energy, electrical energy, nuclear energy, sound energy, light energy. Scope of syllabus. Mechanical energy. Potential energy U is equal to mgh. Derivation included. Gravitational potential energy. Examples. Kinetic energy K is equal to half mv square. Derivation included. Forms of kinetic energy. Translational, rotational and vibrational. Only simple examples. Numerical problems on K and U only in case of translational motion. Qualitative discussions of electrical, chemical, heat, nuclear, light and sound energy. Conversion from one form to another. Common examples. Third, principle of conservation of energy. Scope of syllabus. Statement of the principle of conservation of energy. Theoretical verification that U plus K is equal to constant for a freely falling body. Application of this law to simple pendulum, qualitative only. Simple numerical problems. A. Work, energy and power. Their measurements and units. Work. To understand this chapter, students, you must learn the chapters Motion and Newton's Law. We use the word work in our daily life. The most common is homework, isn't it? Similarly, some daily routine activities such as polishing shoes, washing clothes, watering plants, dusting and sweeping the household, and ironing the clothes, etc. are also termed as work in general sense. However, all of these activities cannot be termed as work in scientific terms. Look at the following examples. 1. Kauser is doing her homework, completes all the assignments given in the school. She feels she has done a lot of work. 2. Iqbal stands holding 10 kilograms of weight on his shoulder. 3. Samir is a computer operator and he spends the day operating the computer. 4. John walks a distance of 5 kilometers for his morning walk. 5. Sachin plays football on the ground. 6. A coolie carries a heavy suitcase from the rickshaw stand to the train. In scientific terms, Kausar, Iqbal, and Samir have hardly done any work. This is because there is no displacement taking place in their activity. John, Sachin, and the coolie have done work. Understanding concept of work. From above examples, we can say the meaning of work in physics is different. Let us see some situations. This is the first situation. A man tries to push the box on the ground with force equal to 10 Newton and it displaces 5 meters. The work done in this case is given as work is equal to force into displacement. 10 Newton into 5 meters. So work is equal to 50 Newton meter. See another example. One day while going to school, the bus failed. The children got down to push the bus to get it started again. The force required to push the bus and the direction of displacement of the bus are in the same direction. The work done in this case is positive work. Now see the second situation. Here one block is on the ground and 2 people are trying to push the box as shown. Here one person pushing the box with a force of 10 Newton towards the right and other one is pushing the box with 5 Newton force to the left. On which side the block will move? Obviously, the box will displace to the right as the force is more there. Let the displacement is 3 meters. Now, the work done by first person can be given as work W is equal to force into displacement. By substituting the values, work is equal to 10 Newton into 3 meters. So work is equal to 30 Newton meters. Here, the force and displacement both are in same direction. Now the work done by other person is given as W is equal to force into displacement. Substituting the values, work is equal to 5 Newton into 3 meters, which equals 15 Newton meter. But here, the force and displacement are not in the same direction. They both are in the opposite direction. So, we write negative sign in work done. Therefore, W is equal to minus 5 Newton into 3 meters, which equals minus 15 Newton meter. See another example. You and your friend are playing with a ball and he throws the ball towards you. You take a catch. The force required to stop the ball acts opposite to the displacement of the ball. The work done in this case is negative. So we can say that when force and displacement are in the same direction, work done is positive. Here, angle between force and displacement is 0 degree. When force and displacement are in the opposite direction, work done is negative. Here, angle between force and displacement is 180 degrees. The third situation. Here, the box is on the ground and there is a wall perpendicular to the ground. If a person tries to push the box with a force of 10 Newton, but due to wall, there is not any displacement, that is, displacement is equal to 0, then what will be the work done? Here, work is equal to force into displacement. So work is equal to 10 Newton into 0, which equals 0. To understand it better, look at this picture. A man is holding a very big box. He is applying large force to hold that box. But here, box is not moving in upward or downward direction. So displacement is 0 and therefore work done is also 0. From all these examples, work is said to be 0 if displacement is 0, no matter how much force is applied. Consider the next situation. Here, box of 10 kilogram moving forward. Let the displacement is 2 meters. We have already studied that the gravitational force is acting on the box in the downward direction, that is, m into g. Therefore, force acting on the box is equal to 10 into 9.8 Newton, which equals 98 Newton. Then work done by the gravitational force is 0. You must have question in your mind, as displacement is non-zero, then why the work done is 0, right? Students, here the force, that is, gravitational force and displacement are at 90 degrees or perpendicular to each other, then work done is 0. When a stone is tied to a string and whirled, means rotated. In a circular path, the string does 0 work on the stone. The displacement of the stone is along the tangent to the circular path. Here, force and displacements are perpendicular to each other. Earth and other planets moving around the sun, and a satellite like Moon or artificial satellite like Chandrayaan-1 moving around the Earth, the work done by the force acting towards the center of the Earth in all these cases is 0. When a simple pendulum is hung by a string in equilibrium, the weight acting downwards and the tension in the string acting upwards balances each other. In this case, no work is done by any force since there is no displacement. Measurement of work. The amount of work done on a body depends on 2 factors. First, the magnitude of the force applied, and second, the displacement produced by the force. If force F1 and F2, where F1 is greater than F2, move 2 different bodies by the same distance, the work done by the force F1 is said to be more than that by the force F2. Similarly, if a force F moves the bodies 1 and 2 by distances S1 and S2 respectively, where S1 is greater than S2, the work done by the force F on body 1 is said to be more than on body 2. Thus, the amount of work done depends on both factors: the magnitude of the force applied and the magnitude of the displacement. The the amount of work done by a force is equal to the product of the force and the displacement of the point of application of the force in the direction of force. That is, work is equal to force into displacement of the point of application of force in the direction of force. In figure, suppose a constant force F displaces a body from position A to position B along its own direction. Then the displacement of the body is AB is equal to S, and the work done is W is equal to F into S. Let this be equation 1. Here we assume that the force does not change during the displacement and it acts so long the body moves. In equation 1, if S is equal to 0, then W is equal to 0. Thus, if a force acts on a body and the body does not move, that is, displacement is 0, then no work is done. Work is a scalar quantity. Expression of work. W is equal to Fs cos theta. It is not necessary that the force always causes the displacement of the body in its own direction. If under some circumstances a force displaces the body in a direction other than the direction of force, then we can determine the amount of work done by the force in two ways. 1. By finding the component of displacement of the body in the direction of force, and 2. By finding the component of force in the direction of displacement. By finding the component of displacement along the force. In figure, suppose a constant force F acts on a body along AB and displaces the body on an inclined surface from A to C. The displacement of the body is AC is equal to S, which is at an angle to the direction of force. To find the component of displacement in the direction of force, that is along AB, a perpendicular CB is drawn from the point C on AB. Then the component of displacement in the direction of force is AB. Hence, work done W is equal to F into AB, but in the right-angled triangle ABC, cos theta is equal to base upon hypotenuse is equal to AB upon AC is equal to AB upon S, or AB is equal to S cos theta. Hence, W is equal to Fs cos theta. Let this be equation 2. Or W is equal to force into component of displacement in the direction of force. By finding the component of force along the displacement. In figure, if PA represents the magnitude and direction of force F acting on the body, then the component of force F in the direction of displacement, that is along AC, is NA. Therefore, work done, W is equal to NA into AC is equal to NA into S. But from right-angled triangle PNA, NA is equal to PA cos theta is equal to F cos theta. Then work done, W is equal to F cos theta into S. Let this be equation 3. Or work is equal to component of force in the direction of displacement into displacement. From equations 2 and 3, it is clear that the work done is equal to the product of, first, magnitude of force F, second, magnitude of displacement S, and third, cosine of the angle between the directions of force F and displacement S, that is cos theta. Note, since force F and displacement S are vector quantities and work W is a scalar quantity, so work is expressed as the dot product or scalar product of force and displacement vectors. The dot product of two vectors is a scalar. In vector form, work done W is written as W is equal to F bar dot S bar. Thus, work done depends on, first, the magnitude of force, second, the magnitude of displacement, and third, the angle between the force and displacement. Case first. If the displacement is in the direction of force, that is theta is equal to 0 degrees, then cos theta is equal to 1. W is equal to F into S. The work done is positive. Examples. 1. In free fall of a body of mass m under gravity through a height h from A to B, the force of gravity F is equal to mg is in the direction of displacement S is equal to h, and the work done by the force of gravity is W is equal to Fs is equal to mgh. 2. A coolie does work on the load when he raises it up against the force of gravity. Both the force exerted by coolie is equal to mg and the displacement is equal to h are in upward direction. The work done by the coolie in raising the load is W is equal to mgh. 3. If a body revolves in a circular path under the influence of a force, on completing one round, the displacement becomes 0. So the work done by the force is W is equal to 0. Case second. If the displacement is normal to the direction of force, that is theta is equal to 90 degrees, then cos 90 degrees is equal to 0. W is equal to 0. Hence, the work done is 0. Examples. 1. When a coolie walks on a horizontal ground while carrying a load on his head, no work is done against the force of gravity because the displacement of load is normal to the direction of force of gravity, which is vertically downwards. Note, the coolie does work against the force of friction when he moves with the load. 2. When a body moves in a circular path in a horizontal plane, no work is done since the centripetal force on the body at any instant is directed towards the center of circular path, and the displacement at that instant is along the tangent to the circular path. That is, normal to the direction of force on the body as shown in figure. It is for this reason that in a circular path, the kinetic energy and hence the speed of the body does not change, although a force acts on the body. Conditions for the work done by a force to be 0. From the above discussion, it is clear that the amount of work done by a force is 0 in the following two situations. 1. When there is no displacement, that is S is equal to 0. And 2. When the displacement is normal to the direction of force, that is theta is equal to 90 degrees. Case third. If the displacement is in a direction opposite to the force, that is theta is equal to 180 degrees, then cos 180 degrees is equal to minus 1. W is equal to minus F into S. The work done is negative. This is usually the case when the force opposes the motion or it tries to stop a moving body. Examples. 1. When a body moves on a surface, the force of friction between the body and surface is in direction opposite to the motion of the body. Therefore, the work done by the force of friction is negative. 2. When a ball of mass m is thrown upwards from A to B to a height h, the displacement h upwards is opposite to the direction of force of gravity mg, that is downwards. So the work done by the force of gravity mg in displacement h is W is equal to minus mgh, that is negative. Note, if the force is variable, that is, force varies during the displacement, the work done is determined by plotting a force displacement graph. The force is taken on y-axis and the displacement s in the direction of the force is taken on x-axis. The area enclosed by the sketch and the displacement axis, that is x-axis, gives the work done. In figure, the force F is directly proportional to the displacement and the graph for force against displacement is an inclined straight line OA. The work done by the force in displacement S is equal to the area of the triangle OAB minus half F into S, which is shown shaded in figure. The method is applicable in all situations. If the force is constant, that is, it does not change with the displacement, the graph will be a straight line parallel to the x-axis as shown in figure, and the area of the rectangle OABC is equal to F into S enclosed between the straight line and the x-axis will be equal to the work done. Work done by the force of gravity W is equal to mgh. Let a body of mass m be moved down through a vertical height h, either directly or through an inclined plane. Example, a hill, slope or stairs. The force of gravity on the body is F is equal to mg, acting vertically downwards, and the vertical displacement in the direction of force is S is equal to h. Therefore, the work done by the force of gravity is W is equal to Fs is equal to mgh. Let this be equation 4. Thus, work done by the force of gravity is same whether the body comes down from a certain height using the stairs or slope or a lift or elevator. Similarly, if a body of mass m goes up through a vertical height h, either directly or through the stairs or slope or lift, the work W is equal to minus mgh is done by the force of gravity on the body, or the work W is equal to mgh is done by the body against the force of gravity. Work definition. Work is the product of force and displacement. In figure, let F be the constant force which acts on an object and S be its displacement in the direction of the force. Let W be the work done. Then, work is the product of force and displacement. The work done W will be given by W is equal to F into S. Work has only magnitude and no direction. Hence, it is a scalar quantity. SI unit of force is Newton and that of displacement is meter. Hence, SI unit of work is Newton meter or joule. It is abbreviated as J. 1 joule. The amount of work done when a force of 1 Newton acting on an object displaces it through a distance of 1 meter along its own direction is called as 1 joule. Bigger units of work are kilojoule, kj, megajoule, mj, gigajoule, gj, where 1 kilojoule is equal to 10 raised to 3 joule, 1 megajoule is equal to 10 raised to 6 joule, and 1 gigajoule is equal to 10 raised to 9 joule. Similarly, in CGS system, the unit is dyne centimeter or erg. 1 joule is equal to 1 Newton into 1 meter. The amount of work done when a force of 1 dyne acting on an object displaces it through a distance of 1 centimeter along its own direction is known as 1 erg. 1 erg is equal to 1 dyne into 1 centimeter. Relation between joule and erg. 1 Newton is equal to 10 raised to 5 dyne and 1 meter is equal to 10 raised to 2 centimeter. 1 joule is equal to 1 Newton into 1 meter, which equals 10 raised to 5 dyne into 10 raised to 2 centimeter. 1 joule is equal to 10 raised to 7 dyne centimeter, which equals 10 raised to 7 erg. Thus 1 joule is equal to 10 raised to 7 erg. Let this be equation 5. Power. We normally use the term power in the sense that a boy has muscle power. A person is powerful. It means that one has large physical strength or may be strong in terms of the power he possesses. But in science, we use power in terms of motors, pumps, engines, etc. Consider some examples. Suppose a 50 kg man takes 5 minutes to go up a staircase, but a 12 kg boy can go up the same staircase in 3 minutes. Then who is powerful and why? We want to fill a tank with water, which is on top of a building. If we try filling it with a bucket, it may require a day to fill it, but a motor or a pump can do this job in just a few minutes. Deepak, Rahul and Ketan wanted to go to the top of a hill. Deepak went walking, Rahul went cycling, and Ketan went by a car, all taking the same route. Ketan reached the top first, then Rahul, and lastly, Deepak reached the top of the hill. Work done by them is the same, but the time required by each one of them is different. Power is the measure of how fast or slow the work is done. If W is the work done in time T, then power, P, is defined as rate of doing work. That is, power is equal to work upon time, which equals W upon T. Thus, the power spent by a source is measured as the amount of work done by the source in 1 second, or it is equal to the rate of doing work by the source. Therefore, P is equal to W upon T. Let this be equation 6. Units of power. The unit of power is watt. This is in honor of James Watt, 1736 to 1819. SI unit. The SI unit of power is watt. It is abbreviated as capital W. If 1 joule of work is done in 1 second, the power spent is said to be 1 watt. That is, 1 watt is equal to 1 joule per second. Bigger units of power are kilowatt, megawatt, and gigawatt, where 1 kilowatt is equal to 10 raised to 3 watt, 1 megawatt is equal to 10 raised to 6 watt, and 1 gigawatt is equal to 10 raised to 9 watt. Smaller units of power are milliwatt and microwatt, where 1 milliwatt is equal to 10 raised to minus 3 watt and 1 microwatt is equal to 10 raised to minus 6 watt. CGS unit. The CGS unit of power is erg per second. Relationship between the SI unit and CGS unit. 1 watt is equal to 1 joule per second, which is equal to 10 raised to 7 erg per second. Horsepower. It is another unit of power largely used in mechanical engineering. It is related to the SI unit watt as below. 1 horsepower is equal to 746 watt, which equals 0.746 kilowatt. Let this be equation 8. Difference between work and power. 1. Work done by a force is equal to the product of force and the displacement in the direction of force. Power of a source is the rate of doing work by it. 2. Work done does not depend on time. Power spent depends on the time in which work is done. 3. SI unit of work is joule. SI unit of power is watt. Energy. Energy as work done. A body capable of doing work is said to possess energy. The energy possessed by a body is measured by the amount of work that the body can perform. When a body does work, its energy decreases, while if work is done on the body, its energy increases. It means that whenever work is done, there is always a transfer of energy. Thus, energy and work are related to each other. We can define energy as follows. The energy of a body is its capacity to do work. Like work, energy is also a scalar quantity. The energy is measured in terms of work, and hence the units of energy and work are same. That is, joules in SI and ergs in CGS system. Different forms of energy. Different forms of energy exist around us. They are heat, light, wind, electric, solar, chemical, sound, and mechanical energy, etc. All energies in this world exist in two forms. 1. Potential energy. 2. Kinetic energy. Potential energy is stored energy in an object, while kinetic energy is energy of motion. Let us focus on mechanical energy and its forms such as kinetic energy and potential energy. Note, there is no transfer of energy if a body is acted upon by a force normal to the direction of its displacement. For example, for a body moving in a circular path, centripetal force is normal to its displacement and work done is zero. That is, there is no transfer of energy. Units of energy. The units of energy are same as that of work. 1. The SI unit of energy is joule and the CGS unit of energy is erg, where 1 joule is equal to 10 raised to 7 erg. 2. The bigger units of energy are, first, watt hour, and second, kilowatt hour. First, watt hour. 1 watt hour, 1 WH, is the energy spent or work done by a source of power, 1 watt, in 1 hour. That is, 1 watt hour is equal to 1 watt into 1 hour, which equals 1 joule per second into 3,600 seconds, which equals 3,600 joule, which equals 3.6 kilojoule. Let this be equation 9. Second, kilowatt hour. 1 kilowatt hour is the energy spent or work done by a source of power, 1 kilowatt in 1 hour. That is, 1 kilowatt hour is equal to 1 kilowatt into 1 hour, which equals 1000 joule per second into 3,600 seconds, which equals 3.6 into 10 raised to 6 joule equals 3.6 megajoule. Let this be equation 10. Note, watt and kilowatt are the units of power, while watt hour and kilowatt hour are the units of work or energy, since power into time is equal to work or energy. 3. Calorie. Heat energy is usually measured in calorie. 1 calorie is the heat energy required in raising the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius or through 1 degree Celsius. It is related to joule as 1 joule is equal to 0.24 calorie or 1 calorie is equal to 4.18 joule. Let this be equation 11. Kilocalorie is a bigger unit of heat energy. 1 kilocalorie is equal to 1000 calories is equal to 4180 joule. 4. Electron volt. The energy of atomic particles is very small, so it is measured in electron volt, EV. 1 electron volt is the energy gained by an electron when it is accelerated through a potential difference of 1 volt. That is, 1 electron volt is equal to charge on an electron into 1 volt, which equals 1.6 into 10 raised to minus 19 coulomb into 1 volt, which equals 1.6 into 10 raised to minus 19 joule, or 1 electron volt is equal to 1.6 into 10 raised to minus 19 joule. Let this be equation 12. Difference between energy and power. 1. Energy of a body is its capacity to do work, while power of a source is the rate at which energy is supplied by it. 2. Energy spent does not depend on time, while power depends on the time in which energy is spent. 3. SI unit of energy is joule or J. SI unit of power is watt or W. Examples. 1. A crane pulls up a car of mass 500 kg to a vertical height of 4 meters. Calculate the work done by the crane. In order to raise the car, the crane has to do work against the force of gravity. Therefore, the force required to lift the car, F, is equal to mg. Is equal to, let's substitute the values. F is equal to 500 into 9.8, which equals 4,900 Newton. Displacement S is equal to vertical height moved, which equals 4 meters. Work done is equal to W is equal to F into S, which equals 4,900 into 4, which equals 19,600 joule. 2. A force of 10 Newton displaces a body by a distance of 2 meter at an angle 60 degree to its own direction. Find the amount of work done. Given F is equal to 10 Newton, S is equal to 2 meter, theta is equal to 60 degrees. Work is equal to force into displacement in the direction of force. Or W is equal to F into S cos theta. Or W is equal to 10 into 2 cos 60 degrees, which is equal to 10 into 2 into half, since cos 60 degrees is equal to 1 by 2. Or W is equal to 10 joule. A boy of mass 40 kgs climbs up a flight of 30 steps each of 20 centimeters high in 2 minutes. And a girl of mass 30 kgs does the same in 1.5 minutes. Compare first the work done and second the power developed by them. G is equal to 10 meter per second square. While climbing, both the boy and girl have to do work against their force of gravity. Force of gravity of boy, F1 is equal to M1G is equal to 40 into 10 is equal to 400 Newton. Force of gravity of girl, F2 is equal to M2G is equal to 30 into 10, which equals 300 Newton. Total height climbed up, H is equal to number of steps into height of each step, which equals 30 into 20 centimeters, which equals 600 centimeters, or 6 meters. First, work done by the boy. W1 is equal to F1 into H, which equals 400 into 6, which equals 2400 joule. Work done by the girl. W2 is equal to F2 into H is equal to 300 into 6, which is equal to 1800 joule. W1 is to W2 is equal to 2400 is to 1800, which is equal to 4 is to 3. Second, power developed is equal to work done upon time taken. Here, T1 is equal to 2 minutes is equal to 120 seconds. T2 is equal to 1.5 minutes is equal to 90 seconds. Power developed by boy, P1 is equal to W1 upon T1, that is 2400 joule upon 120 second, that is equal to 20 watts. Power developed by girl, P2, is equal to W2 upon T2 is equal to 1800 joule upon 90 seconds is equal to 20 watts. P1 is to P2 is equal to 20 is to 20 is equal to 1 is to 1. Alternative. First, since height climbed is same, therefore W1 upon W2 is equal to M1GH upon M2GH is equal to M1 upon M2, which is equal to 40 upon 30, which is equal to 4 upon 3. Second, P1 upon P2 is equal to W1 upon T1 upon W2 upon T2, that is equal to W1 upon W2 into T2 upon T1, that is equal to 4 upon 3 into 1.5 upon 2, that is equal to 1 upon 1. 4. A force of 15 Newton is required to pull up a body of mass 2 kgs through a distance 5 meters along an inclined plane, making an angle of 30 degrees with the horizontal as shown in figure. Calculate first the work done by the force in pulling the body. Second, the force due to gravity on the body. Third, the work done against the force due to gravity. Take G is equal to 9.8 meter per second square. Fourth, account for the difference in answers of part first and part third. First, work done by the force in pulling the body up, W is equal to force into displacement in the direction of force is equal to 15 Newton into 5 meters, which equals 75 joule. Second, force due to gravity on the body, F is equal to mg, is equal to 2 into 9.8, which equals 19.6 Newton. Third, work done against the force due to gravity, W dash, is equal to force due to gravity into vertical height moved, is equal to mg into bc. But in right-angled triangle ABC, sine 30 degree is equal to BC upon AB. BC is equal to AB sine 30 degrees. Hence, W dash is equal to mg into AB sine 30 degrees, which is equal to 19.6 into 5 into 1 by 2, since sine 30 degrees is equal to 1 by 2, which is equal to 49 joule. Fourth, we note that W is greater than W dash. The difference in work W and W dash is 75 joule minus 49 joule is equal to 16 joule. Actually, 16 joule is the work done against the force of friction between the body and the inclined plane. Five, calculate the power of an engine required to lift 10 raised to 5 kgs of coal per hour from a mine 360 meters deep. Take G is equal to 10 meters per second square. Given M is equal to 10 raised to 5 kgs, G is equal to 10 meters per second square, H is equal to 360 meters, T is equal to 1 hour, which is equal to 60 into 60 seconds, which is equal to 3,600 seconds. The work needed in lifting a mass M to a height h against the force due to gravity is W is equal to mg into h, which is equal to mgh, and power P is equal to work done upon time taken is equal to mgh upon t. Therefore, P is equal to 10 raised to 5 into 10 into 360 upon 3600, that is equal to 10 raised to 5 watts, that is equal to 100 kilowatts. Note, in fact, the actual power of the engine will be much more than 100 kilowatt because, first, some energy will get wasted in overcoming the force of friction, and second, the efficiency of the engine will always be less than 100%. Six, an electric motor of power 100 watt is used to drive the stirrer in a water bath. If 50% of the energy supplied to the motor is spent in stirring the water, calculate the work done on water in 1 minute. Given power supplied is equal to 100 watts, time t is equal to 1 minute, which equals 60 seconds. Power used in stirring the water is equal to 50% of the power supplied is equal to 50 upon 100 into 100 watt is equal to 50 watt. Work done on water is equal to power used into time, which equals 50 watt into 60 seconds, which equals 3000 joule. Seven, a man exerts a force of 200 Newton in pulling a cart at a constant speed of 16 meters per second. Calculate the power spent by man. Given force is equal to 200 Newton, velocity is equal to 16 meters per second. Power is equal to force into velocity, which equals 200 Newton into 16 meters per second, which is equal to 3200 watt. Eight, the work done by the heart is 1 joule per beat. Calculate the power of the heart if it beats 72 times in 1 minute. Given number of beats in 1 minute is equal to 72. Therefore, number of beats per second is equal to 72 upon 60, which equals 1.2. Power of heart is equal to work done per second is equal to work done per beat into number of beats in 1 second. Substituting the values is equal to 1 joule into 1.2 beats per second, which equals 1.2 joule per second or 1.2 watt. Nine. Express 5 kilowatt into joule. 1 kilowatt hour is equal to 1000 watt into 60 into 60 second, which equals 3.6 into 10 raised to 6 joule. Therefore, 5 kilowatt hour is equal to 5 into 3.6 into 10 raised to 6 joule, which equals 1.8 into 10 raised to 7 joule. 10. The energy of an electron is 4.0 into 10 raised to minus 19 joule. Express it in electron volt. Since 1 electron volt is equal to 1.6 into 10 raised to minus 19 joule, therefore 4.0 into 10 raised to minus 19 joule is equal to 4.0 into 10 raised to minus 19 upon 1.6 into 10 raised to minus 19 electron volt is equal to 2.5 electron volt. B. Different forms of energy. Mechanical energy and its different forms. The energy possessed by a body due to its state of rest or of motion is called the mechanical energy. It has two forms. 1. Potential energy and 2. Kinetic energy. The total mechanical energy of a body is the sum of its potential energy and kinetic energy. Potential energy, U. The energy possessed by a body at rest in its changed position or change in size and shape is called the potential energy. It is usually denoted by the symbol U. Examples: a body placed at a height above the ground, a wound-up watch spring, a compressed spring, a bent bow, a stretched rubber string, etc. have the potential energy. Forms of potential energy. In mechanics, potential energy is mainly of two kinds. 1. Gravitational potential energy due to its changed position, and 2. Elastic potential energy due to its changed size and shape. 1. Gravitational potential energy. Each body experiences a force of attraction due to Earth, which is called the force due to gravity or weight of the body. The potential energy possessed by a body due to the force of attraction of Earth on it is called its gravitational potential energy. The gravitational potential energy of a body is zero when it is at infinity because the force of attraction of Earth on the body is then zero. The gravitational potential energy of a body at a point is the amount of work done by the force of attraction of Earth in bringing that body from infinity to that point. Since work is done by the force of gravity itself, so at a finite distance from Earth, the gravitational potential energy of the body is negative. As the distance of body from the surface of Earth increases, the force of attraction of Earth decreases and its gravitational potential energy increases. That is, the negative value of gravitational potential energy decreases. Two, elastic potential energy. When an external force is applied on a non-rigid body, it gets deformed due to change in its size and shape. On removal of the force, it regains its original form due to the property of elasticity. Some work is done by the external force in deforming the body. This work is stored in the body in the form of its elastic potential energy. Thus, the potential energy possessed by a body in the deformed state due to change in its size and shape is called the elastic potential energy. It is work done in deforming the body or in changing the size and shape of the body. Gravitational potential energy at a height, U is equal to mgh. The gravitational potential energy of a body at a height above the ground is measured by the amount of work done in lifting it up from the ground to that height against the force of gravity, assuming that its gravitational potential energy on the ground is zero. When a body of mass m is raised to a height h above the ground level, the force acting on the body is the gravitational pull of the Earth and equal to mg. This force acts in the vertically downward direction. To lift the body above the surface of the Earth, we will have to work against this force of gravity. Work is equal to force into displacement. Therefore, F is equal to mg and S is equal to h. W is equal to m into g into h, which equals mgh. This work done on the body is actually the increase in potential energy of the body. Hence, this work done is equal to potential energy. Therefore, gravitational potential energy U is equal to mgh. Let this be equation 13. Thus, when a body is thrown vertically upwards, it rises up, so the height of the body from the ground increases. Hence, its potential energy increases. Similarly, when a body is released from a height, it falls down, so the height of the body from the ground decreases. Hence, its potential energy decreases and it becomes zero at the Earth's surface. When a body of mass m is taken up from a height h1 to a height h2 above the ground, h2 greater than h1, the gain in potential energy is equal to final potential energy minus initial potential energy, which equals mgh2 minus mgh1 is equal to mg into h2 minus h1. But if a body of mass m falls down from a height h1 to a height h2 above the ground, h2 less than h1, H2 being less than H1, loss in potential energy is equal to initial potential energy minus final potential energy is equal to mg into H1 minus H2. Note, precisely mgh is the gain in potential energy of the body when it is raised to a height h above the ground. But here we have assumed that when the body is on the Earth's surface or ground, its gravitational potential energy is zero, so we consider the gravitational potential energy of the body at height h equal to mgh. Kinetic energy. The energy possessed by a body due to its state of motion is called the kinetic energy. It is usually denoted by the symbol K. Examples: a fast-moving stone has the capacity of breaking a window pane on striking it, and thus it has the kinetic energy. Similarly, a car in motion, moving hands of a clock, the bullet fired from a gun, a rolling ball, an apple falling from a height, etc. have the kinetic energy. Expression for the kinetic energy: K is equal to 1 by 2 mv square. The kinetic energy possessed by a moving body is equal to the amount of work which the moving body can do before coming to rest. It can be calculated by the amount of work done by an opposing force to stop the body. Suppose a body of mass m is moving with a velocity v. It is brought to rest by applying a constant opposing force F. Let A be the uniform retardation produced by the force, and the body travels a distance s before coming to rest. Then retarding force F is equal to mass into retardation is equal to ma. Let this be equation first. Kinetic energy of the body is equal to work done by the retarding force F in displacement s before stopping it. Or kinetic energy K is equal to retarding force F into displacement s. Or K is equal to F into S. Let this be equation second. Now, to calculate the displacement S, we have initial velocity u is equal to v, final velocity v is equal to 0. Since a is the retardation, so acceleration is equal to minus a. From the relation v square is equal to u square plus 2as, 0 is equal to v square minus 2as. Therefore, displacement s is equal to v square upon 2a. Let this be equation third. Substituting the values of f and s from equations first and third in equation second, we get kinetic energy K is equal to F into S is equal to ma into v square upon 2a, which equals 1 by 2 mv square, or K is equal to 1 by 2 mv square. Kinetic energy is equal to 1 by 2 mass into velocity square. Let this be equation 14. Thus, kinetic energy of a body depends on square of its velocity of motion. On doubling the velocity of motion of a body, its kinetic energy becomes 4 times. In other words, a faster moving body has more kinetic energy than a slowly moving body of same mass. Relationship between kinetic energy and momentum. Let a body of mass m be moving with a velocity v. then its kinetic energy K is equal to 1 by 2 mv square. Let this be equation first. Momentum P is equal to mv. Let this be equation second. Substituting the value of V is equal to P by M from equation second in equation first, we get K is equal to 1 by 2 M into P upon M square is equal to P square upon 2M, or P square is equal to 2 mk. Thus, kinetic energy K and momentum P are related as P is equal to under root 2 mk, or K is equal to P square upon 2M. Let this be equation 15. Case first. If a light body A of mass small m and a heavy body B of mass capital M both have same momentum P, then the kinetic energy of the light body A will be more than that of the heavy body B. Ka upon Kb is equal to P square by 2 small m upon P square by 2 capital M, which equals capital M upon small m. Since capital M is greater than small m, so Ka is greater than Kb. Case second. If a light body A of mass small m and a heavy body B of mass capital M have the same kinetic energy K, then the heavy body B will have more momentum than that of the light body A. Pb upon Pa is equal to under root 2 capital Mk upon under root 2 small mk is equal to under root capital M upon small m. Since capital M is greater than small m, so Pb is greater than Pa. Work energy theorem. When a force is applied in the direction of motion of a body, it accelerates the motion and thus increases the kinetic energy of the body. This increase in kinetic energy is equal to the work done by the force on the body. This is called the work energy theorem. Thus, according to the work energy theorem, the work done by a force on a moving body is equal to the increase in its kinetic energy. Proof. Let a body of mass m be moving with an initial velocity u. When a constant force F is applied on the body along its direction of motion, it produces an acceleration A, and the velocity of the body changes from u to v in moving a distance s. Then, force F is equal to mass into acceleration is equal to ma. Let this be equation first. Work done by the force is equal to force into displacement, or W is equal to F into S. Let this be equation second. From relation V square is equal to U square plus 2AS, displacement S is equal to V square minus U square upon 2A. Let this be equation third. Substituting the values of F and S from equations first and third in equation second, we get W is equal to ma into V square minus U square upon 2A is equal to 1 by 2m into V square minus U square, or W is equal to 1 by 2 mv square minus 1 by 2 mu square. Let this be equation 16. But initial kinetic energy Ki is equal to 1 by 2 mu square. And final kinetic energy, Kf, is equal to 1 by 2 mv square. Then from equation 16, W is equal to Kf minus Ki. Thus, work done on the body is equal to increase in kinetic energy. Let this be equation 17. Forms of kinetic energy. A body can have three types of motion, namely the translational motion, rotational motion, and vibrational motion. So, the kinetic energy is also of three forms. 1. Translational kinetic energy. 2. Rotational kinetic energy. And 3. Vibrational kinetic energy. 1. Translational kinetic energy. The motion of a body in a straight line path is called the translational motion, and the kinetic energy of the body due to motion in a straight line is called the translational kinetic energy. Examples: a car moving in a straight path, a freely falling body, a molecule of monoatomic gas have the translational kinetic energy. 2. Rotational kinetic energy. If a body rotates about an axis, the motion is called the rotational motion, and the kinetic energy of the body due to rotational motion is called the rotational kinetic energy, or simply the rotational energy. Examples: a spinning top, a rotating wheel, and a rotating fan have the rotational kinetic energy. The Earth rotating on its own axis has a huge amount of rotational kinetic energy. The atoms in a diatomic or polyatomic molecule rotate about a fixed axis in addition to their translational motion, so they possess both the rotational and translational kinetic energies. 3. Vibrational kinetic energy. If a body moves to and fro about its mean position, the motion is called the vibrational motion. The kinetic energy of the body due to its vibrational motion is called vibrational kinetic energy, or simply vibrational energy. Examples: a wire clamped at both the ends, when struck in the middle, vibrates. The energy possessed by the wire is the vibrational kinetic energy. A steel strip clamped at one end vibrates when the other free and is slightly displaced and then released. The steel strip is then said to possess the vibrational kinetic energy. In a solid, the atoms vibrate about their mean positions, so they possess the vibrational kinetic energy. In a polyatomic molecule, the atoms can vibrate about their mean positions, so a polyatomic molecule has the vibrational energy in addition to the rotational and translational energies. Note: depending upon its state of motion, a moving body may possess either one or more than one form of kinetic energy simultaneously. For example, a rolling ball and the wheel of a running vehicle have both the translational and rotational kinetic energies simultaneously. Distinction between the potential energy and kinetic energy. 1. Potential energy is the energy possessed by a body due to its changed position or changed size and shape, while kinetic energy is the energy possessed by a body due to its state of motion. 2. Potential energy is equal to the work done in bringing the body to its changed state. Kinetic energy is equal to the work that a moving body can do before coming to rest. 3. Potential energy can change only in form of kinetic energy, while kinetic energy can change into any other form. 4. Potential energy does not depend on the speed of the body, while kinetic energy depends on the speed of the body. Conversion of potential energy into the kinetic energy. Potential energy changes into the kinetic energy whenever it is put to use. Examples: 1. A stone at a height has the gravitational potential energy which is equal to the work done in moving the stone to that height against the force due to gravity on it. When the stone is made to fall on a nail standing on a wooden piece, the nail begins to penetrate. The reason is that as the stone starts falling, its potential energy begins to change into its kinetic energy. The falling stone now has both potential and kinetic energy. When it strikes the nail, stone does work on the nail. The kinetic energy of the stone changes into the kinetic energy of the nail, due to which the nail moves into the wooden piece. 2. A wound-up watch spring has the elastic potential energy which is equal to the work done in bringing it to the wound-up state. As the spring unwinds itself, the potential energy stored in it changes into the kinetic energy, which does work in moving the hands of the watch and thus changes into the kinetic energy of the hands. Three. When the string of a bow is pulled, some work is done which is stored in the deformed state of the bow in the form of its elastic potential energy. On releasing the string to shoot an arrow, the potential energy of the bow changes into the kinetic energy of the arrow, which makes it move. 4. A compressed spring has the elastic potential energy due to its compressed state. When it is released, the potential energy which does work on the ball placed on it and changes into the kinetic energy of the ball, due to which it flies away. Different forms of energy. Nature has provided us energy in the various forms, namely 1. Solar energy, 2. Heat or radiant energy, 3. Light energy, 4. Chemical or fuel energy, 5. Hydro energy, 6. Electrical energy, 7. Nuclear energy, 8. Geothermal energy, 9. Wind energy, 10. Sound energy, 11. Magnetic energy, and 12. Mechanical energy, etc. These forms of energy are described below. 1. Solar energy. The energy radiated out by sun is called the solar energy. Solar energy cannot be directly used to perform work because it is too diffused and it is not always available uniformly. However, a number of devices such as first, solar panels, second, solar furnaces, and third, solar cells, etc. have been invented to make use of solar energy. First, a solar panel consists of a black painted metal surface which absorbs the sun's energy and heats water in its contact. Second, a solar furnace has a parabolic mirror used to focus the sun's rays on a small area so that a high temperature is achieved. Thus, by keeping water at the focus of mirror, water can be boiled to produce steam, and steam can then be used to drive the turbine of an electric generator so as to obtain the electrical energy. Third, the solar cells are used to convert the solar energy directly into the electrical energy. These cells are made from the thin slices of semiconducting material. However, the efficiency of a solar cell to convert solar energy into the electrical energy is very low. Two, heat energy. The energy released on burning coal, oil, wood, or gas is called the heat energy. The steam obtained on heating water possesses heat energy and it has the capacity to do work. In a steam engine, heat energy of steam is used to obtain work, that is mechanical energy. Sun is also a source of heat energy. We on Earth receive heat energy directly from the sun. 3. Light energy. It is the form of energy in presence of which other objects are seen. The natural source of light energy is sun. The moon reflects the sunlight at night. Many sources such as fire, burning candle, etc. also give light energy along with the heat energy. Four, chemical or fuel energy. The energy possessed by the fossil fuels such as coal, petroleum and natural gas is called the chemical energy or fuel energy. These fuels contain chemical energy stored in them. When fuels are burnt, the chemical energy changes into the heat and light energy. The food that we eat also has the chemical energy in it. Plants convert the solar energy into the chemical energy of food during the process of photosynthesis. A battery has the chemical energy stored in it and it provides the electrical energy when in use by a chemical reaction which takes place inside it. Five, hydro energy. The energy possessed by the fast-moving water is called hydro energy. This energy is used to generate electricity in hydroelectric power stations. For this, water is stored in the dams built across the rivers high up in the hills, and the water from the dams is allowed to flow down through pipes. The kinetic energy of the fast-flowing water drives the turbines of the generators to produce electrical energy. 6. Electrical energy. When two dry bodies are rubbed together, they get charged due to movement of free electrons from one body to the other body, so they possess electrical energy. In an electric cell, due to movement of ions from one electrode to the other electrode within the cell, as a result of chemical reaction, it becomes a source of electrical energy. Seven, nuclear energy. The energy released due to loss in mass during the processes of nuclear fission and fusion is called the nuclear or atomic energy. In both these processes, the loss in mass gets converted into energy in accordance with the Einstein mass-energy relation E is equal to mc square. This energy is used in nuclear reactors for the constructive purpose to produce electrical energy and is used in atom bomb for the destructive purpose to produce heat and other forms of energy so as to destroy the enemy in war. 8. Geothermal energy. The energy released in nuclear disintegrations in the interior of Earth gets stored deep inside the Earth and is called the geothermal energy. This energy heats up the underground water to produce the natural steam. Sometimes the natural steam may burst out from the surface of Earth as hot springs. The electric power companies may drill wells into the Earth to trap the natural steam, which may be used to run the turbines of generators to produce electricity. Nine. Wind energy. The energy possessed by the fast-moving air, that is, storm, is called the wind energy. This energy is used in driving a windmill. In past, for many years in rural areas, windmills were used to pump out the underground water and to grind grains. Nowadays, large giant windmills are being used to drive the turbine of electric generators for producing electricity. 10. Sound energy. A vibrating body possesses the sound energy. It is sensed by our ears. When the disturbance produced by a vibrating body in the atmospheric air layers reaches our ears and produces vibrations in the ear membrane, sound is heard. 11. Magnetic energy. The energy possessed by a magnet, due to which it can attract iron filings, is called the magnetic energy. An electromagnet has the magnetic energy. 12. Mechanical energy. The energy possessed by a body due to its state of rest or of motion is called the mechanical energy. A body at a height, a moving body, a stretched bow, etc. have the mechanical energy. Conversion of one form of energy into the other form. In our daily life, we require energy in various forms. Since one form of energy can be converted into the other form, we can obtain the energy in the required form from the form of energy available to us. Figure shows some examples of conversion of energy from one form to the other form. Dynamo converts mechanical energy into electrical energy. Motor converts electrical energy into mechanical energy. In electric iron, electric energy is converted into heat energy, while in thermocouple, heat energy is converted into electrical energy. In loudspeaker, electrical energy is converted into sound energy, while microphone converts sound energy into electrical energy. Charging a battery converts electrical energy into chemical energy. Cell in use converts chemical energy into electrical energy. When candle is lighted, chemical energy is converted into light energy. When in presence of sun, that is light energy, in process of photosynthesis in plants, get converted into chemical energy, that is food. In lighted electric bulb, electric energy converts in light energy. In photocell, light energy converts in electrical energy. Now we consider below some more examples of conversion of one form of energy into the other form. 1. Mechanical energy to electrical energy. The water stored in the reservoir of a dam has the potential energy. When water flows down, its potential energy decreases and kinetic energy increases. If the falling water is made to rotate a turbine near the bottom of the dam, the kinetic energy of water is transferred to the turbine in the form of rotational kinetic energy, due to which it rotates. The turbine rotates the armature of the generator connected to it, and thus the kinetic energy gets transformed into the electrical energy in the generator. Thus, an electric generator or a dynamo converts the mechanical energy into the electrical energy. Two, electrical energy to mechanical energy. In an electric motor, when an electric current is passed in a coil freely suspended or pivoted in a magnetic field, a torque acts on the coil due to which it rotates. The shaft attached to the coil also rotates with it. Thus, the electrical energy changes into the mechanical energy. The electric motor is used in many home appliances such as electric fan, washing machine, mixer, grinder, etc. It is also used to run the industrial machines. 3. Electrical energy to heat energy. In electric appliances such as heater, oven, geyser, toaster, etc., electrical energy changes into the heat energy when a current passes through their resistance wire or filament. 4. Heat energy to electrical energy. In a thermocouple, when two junctions of two different metals are kept at different temperatures, one junction is kept hot while the other cold, a current flows in the thermocouple. Thus, a thermocouple changes the heat energy supplied at the hot junction into the electrical energy. Five. Electrical energy to sound energy. A loudspeaker, when in use, receives electrical energy in form of electrical signals from the microphone and changes it into the sound energy. In an electric bell, when an electric current is passed, the electrical energy changes into the sound energy. 6. Sound energy to electrical energy. A microphone converts the sound energy into the electrical energy in form of varying electric signals. 7. Electrical energy to chemical energy. While charging a battery, the electrical energy changes into the chemical energy of the cell. 8. Chemical energy to electrical energy. From an electric cell, when current is drawn, the chemical energy stored in it changes into the electrical energy. 9. Chemical energy to light energy. When a candle burns, it gives light. Similarly, in a kerosene lamp, when the oil soaked in its wick burns, the chemical energy changes into the light energy. 10. Light energy to chemical energy. The light energy from sun is absorbed by the green plants and they change it in form of the chemical energy, food, during the process of photosynthesis. 11. Electrical energy to light energy. When an electric bulb glows on passing an electric current through it, the electrical energy changes into the heat and light energies. 12. Light energy to electrical energy. In a photoelectric cell, the light energy gets converted into the electrical energy. In a solar cell, the light or solar energy changes into the electrical energy. (13) Heat energy to mechanical energy. In a steam engine, the heat energy of steam changes into the kinetic energy of piston. 14. Chemical energy to heat energy. When fuels such as wood, coal, biogas, etc. burns, the chemical energy changes into heat energy. In a steam engine, the chemical energy of coal on burning changes into the heat energy of steam. In explosion of crackers, the chemical energy changes into the heat, light, and sound energies. In lighting a candle or matchstick, the chemical energy changes into the heat and light energies. In respiration, the chemical energy converts into the heat energy. 15. Chemical energy to mechanical energy. In automobiles, while in motion, the chemical energy of petrol or diesel changes into the mechanical energy or kinetic energy. (16) Electrical energy to magnetic energy. While making an electromagnet, an electric current is passed in a coil wound around a soft iron bar which gets magnetized. Thus, the electrical energy changes into the magnetic energy. 17. Nuclear energy to electrical energy. In a nuclear reactor, the energy released in the process of nuclear fission is the nuclear energy which is converted into the electrical energy. 18. Mechanical energy to heat energy. When water falls from a height, the potential energy stored in water at that height changes into the kinetic energy of water during the fall. On striking the ground or bottom, a part of the kinetic energy of water changes into heat energy, due to which the temperature of water rises. The moving parts of a machine get heated due to friction. Thus, a part of mechanical energy changes into heat energy. Note 1. Whenever mechanical energy changes to other forms, it is always in the form of kinetic energy and not in the form of potential energy. That is, the stored potential energy first changes to kinetic energy and then kinetic energy changes to the other form. 2. Degraded energy. While transformation of energy from one form to the other desired form, the entire energy does not change into the desired form, but a part of it changes either to some other undesirable form, usually heat due to friction, or a part is lost to the surroundings due to radiation, which becomes useless. This conversion of energy to the undesirable or non-useful form is called the dissipation of energy. Since this part of energy is not available to us for any productive purpose, so we call this part of energy as the degraded form of energy. Examples: 1. When a bulb is lighted using the electrical energy, a major part of it is lost in the form of heat energy. Only a small part converts into the useful light energy. 2. When a vehicle is run by using the chemical energy of its fuel, a major part is wasted in the form of heat and sound energies. Only a small part of chemical energy changes into the useful mechanical energy. Examples: 1. A body of mass 5 kg is taken from a height 5 meters to 10 meters. Find the increase in its potential energy. G is equal to 10 meter per second square. Given m is equal to 5 kg, H1 is equal to 5 meters, H2 is equal to 10 meters, G is equal to 10 meter per second square. Increase in potential energy is equal to mg into H2 minus H1. Let's substitute the values. Is equal to 5 into 10 into 10 minus 5, which equals 250 joules. Examples. 2. A body of mass 1 kg falls from a height of 5 meters. How much energy does it possess at any instant? Take G is equal to 9.8 meter per second square. Given M is equal to 1 kg, H is equal to 5 meters, G is equal to 9.8 meter per second square. The energy possessed by the body at any instant is equal to initial potential energy of the body is equal to mgh. Let's substitute the values. It is equal to 1 into 9.8 into 5, which is equal to 49 joules. Examples. 3. 500 liters of water is raised from the first floor of a house at height 4 meters to its third floor at height 12 meters. State whether the potential energy of water will decrease or increase. Find the decrease or increase in potential energy of water. Take G is equal to 10 Newton per kg. Density of water is equal to 1 kg per liter. Given mass of water M is equal to volume into density is equal to 500 liters into 1 kg per liter is equal to 500 kgs. H1 is equal to 4 meters, H2 is equal to 12 meters, G is equal to 10 Newton per kg. Since height of water above the ground increases, H2 is more than H1, so the potential energy of water will increase. Increase in potential energy is equal to mg into H2 minus H1. Let's substitute the values. It is equal to 500 into 10 into 12 minus 4, which equals 4 into 10 raised to 4 joules. C. Conservation of energy. Principle of conservation of energy. According to the principle of conservation of energy, energy can neither be created nor can it be destroyed. It only changes from one form to the other. In universe, energy occurs in various forms. The sum of all forms of energy in the universe remains constant. When there is a transformation of energy from one form to another, the total energy always remains same, that is, it remains conserved. If there is only an interchange between the potential energy and kinetic energy, the total mechanical energy, that is the sum of kinetic energy K and potential energy U, remains constant. That is, K plus U is equal to constant when there are no frictional forces. The principle of conservation of energy is one of the fundamental principles of nature. Freely falling body. Theoretical verification of K plus U is equal to constant for a freely falling body. Let a body of mass m fall freely under gravity from height h above the ground. Let us calculate kinetic energy and potential energy at various positions, say A, at height h above the ground level, and B, when the body has fallen a distance x, and at C, on the ground. figure. 1. At position A, the initial velocity of the body, u, is equal to 0 since the body is at rest. Therefore, kinetic energy is equal to half mv square is equal to 0. Potential energy is equal to mgh. Therefore, total energy is equal to 0 plus mgh, which equals mgh.